pleasure to introduce our last speaker for today, Ramon Barral.
Thank you.
The title of his talk is, well, you can read it here. You are from?
Huh?
What is the name of the
university? It's Ritsumeikan from Japan. Well, first, I should thank the organizers for inviting me. It's my honor to be here today. Also, just know I gave this talk like 3 or 4 times already, and I just noticed I don't know how to pronounce this. It's supposed to be Devaney or? Okay, because I always say Devaney, but this is the Spanish reading.
No, not Devaney.
Okay, so so it's about Devaney chaos for foliated spaces. So as the title implies, what I'm going to do is I'm going to take this concept from topological dynamics. If you don't know the definition, I'll give it in a second. So I'm going to use the usual machinery of pseudogroups and all that. I'm going to try to generalize this to define it for foliated spaces. So basically, if you're thinking, why is that interesting? Well, what I wanted to do, but I still haven't gotten to it, is that usually in topological dynamics, there's several different definitions of what chaos should be, right? So you have Devaney chaos, which is probably the most commonly used. Then there's like linear chaos, you have positive entropy, so you have many different things, right? And usually what's interesting is you get 1 or 2 of those and you show that in some context implies the other. So you can say, for example, so Devaney chaos and shadowing imply positive entropy, let's say. So what I think it would be interesting is like doing something like that in the foliated case. And of course, we have all the definition and the work on topological entropy due to, as mentioned, G's, Langevin, and Balzac. So hopefully in the future we can get some result like that, which can connect both definitions of chaos. So I guess that's it. And let's start. So we will start by so how the talk will go is like I first introduce some basic notions from topological dynamics. Then I'm gonna explain a little bit how to generalize them to pseudogroups and foliated spaces, and why that's not entirely trivial. And basically later I will more or less state my results, which imply that for compact foliated spaces, everything more or less works as for group actions if you want. But in the non-compact case, there's some interesting phenomena which can be illustrated by several examples. So that's more or less the outline of the talk. By the way, I have 50 minutes, right? Okay. I mean, I'll try to be fast, though. Okay, so let's start. So in case you don't know, we start by defining sensitivity to initial conditions. So you have your metric space, and you have a map, which you can consider continuous or something. So you have the definition of sensitivity is if there's some constant such that for any point on any radius, you can find a point close enough and some iterate of the map such that the images are at least C apart. So if I draw here, everybody can see, right? So you take any point you want and any ball, and inside that ball, you can find another point and an iterate such that they go far apart, right? Distance C. And usually somebody asks, so this is not the same as expansivity where you can separate any 2 given points. Here, this just says that for any point, you can find points close enough that you can separate. Well, this is trivial to generalize to group actions. You just change these FNs to Gs, basically. And sensitivity is usually, in several definitions of chaos, they feature some sort of sensitivity. And in fact, if we look at Edward Lorenz, where he was, one of the founders, I guess, of modern chaos theory, he said, chaos is when the present determines the future, but the approximate present does not approximately determine the future, which is basically more or less this picture here. Anyway, it's well known that he was studying, I think, weather prediction or something. And there was some rounding error, and then the predictions became wildly different, and he came up with this kind of thing. So then Devaney gave this definition of chaos. So again, we have a map on a metric space, and the condition, his definition of chaos has three conditions. The first one is that for any non-empty open sets, U and V, there is some image of U that intersects V, and this is called topological transitivity. And usually, for weird spaces, this is the same as having one dense orbit. So you can think of that if you want. The second condition is that there is a dense subset of periodic points. So F has density of periodic orbits, EPO. And finally, the third condition is that what we just stated before is that F is sensitive to initial conditions. So if we look at this, I read like his book, and in the book, when he introduces his definition, he says that basically this condition is sort of states that the system cannot be topologically decomposed into two separate parts. This third condition is more or less like the butterfly effect or whatever, the quote I showed before by Edward Lorenz. So the interpretation of this is more or less clear. And then this condition, in his own words, he said it's like some sort of regularity. Usually periodic orbits imply regularity, but if you mix them with weird things, then something else can happen. So basically, the idea is that most of the chaotic content of this definition it seems to be encapsulated here, right? But however, it was later proved that actually the third condition is redundant. So when you have the first two, then this topological transitivity mixed with periodic orbits already implies that the system is sensitive. So this condition is redundant. And this is for maps, and is for groups, and semi-groups even. And this is also true when X is not compact. I think if it's just a metric countable, like a separable metric space or something like that, this also works. I mentioned this because in the foliated setting, we're going to see that compactness is a very important condition. And several other basic definitions. So we have a dynamical system, and then now we were talking about basically sensitivity, right? And more or less, the opposite of sensitivity is equicontinuity. So in the sensitivity, you can separate nearby points, but in continuity, this expansion is uniformly bounded. So there's some assignment epsilon delta, such that the images of balls of radius delta around X are always contained in balls of radius epsilon of the image. So there's no like this unbounded expansion. And if every point is a point of equicontinuity, then the system is equicontinuous. And if furthermore X is compact, then this assignment is uniform. And if the points of equicontinuity are dense, but not the entire space, then you get almost equicontinuity. And finally, I should mention, because we're going to generalize this too, this theorem by Auslander and York, it's called usually Auslander-York dichotomy, says that if we have a compact metric space and a map, and the system is topologically transitive, then so basically the idea is that this dichotomy expresses mathematically the intuitive notion that chaos and equicontinuity are like complete opposites, right? So it says as soon as the system is topologically transitive, then it's either sensitive or almost equicontinuous. And moreover, if F is minimal, so every orbit is dense, then actually it's either sensitive or equicontinuous. Okay, so I think that's all the preliminaries, for topological dynamics. So we have these things. We have first the definition of Devaney chaos. We have this theorem that the first two conditions imply the third one, and finally we have the this Auslander-York dichotomy, and we want to generalize and study all these three things for foliated spaces. So that's this. And we're going to use pseudogroups as, this is probably obvious to this audience, but we're going to use pseudogroups as dynamical models, right? So we want to give a definition of sensitivity and Devaney chaos for foliated spaces, compare it to the results for group actions, and obtain some interesting examples. That's more or less the idea. Okay, Just say, I guess everybody knows this here, but I guess it's the sort of no man left behind approach. So I just mentioned it. A foliated space is like a foliation, but the transversals don't have to be manifolds. So these are like famous attractors. So for example, very easy, if you take a solid torus and you embed it inside itself, wrapping around the hole twice, like this, then in the limits, you get something that is a product locally of the real line and a Cantor set, but it's still like divided, so partitioned into leaves, right? Like a foliation. So this is the kind of things that we're gonna work in a general scenario where we can have these things in addition to normal foliations. If you're not familiar with it, just think of a foliation. And of course, this is also well known. It's an old story. So foliated spaces are generalized dynamical systems where the leaves are more or less the orbits, right? So I should mention that I'm not the first person to study chaos for foliated spaces. So even as I mentioned, so I should mention that, as I said, there's many definitions of chaos. So for example, one can regard like the work on topological entropy as chaos for foliated spaces. But if I'm correct, they never actually in those papers they never use this term, I think. But after that, there's been some papers that actually use the term chaotic foliated space. And there's two. First one is by Churchill, who was a physicist, which is strange. He was studying general relativity, and he defined chaos for a foliation with this condition. So if it has a dense leaf and the set of compact leaves is dense. So basically, he took the Devaney chaos definition, and this is, of course, corresponds to topological transitivity, and this corresponds to density of periodic orbits. And he said, well, in the group case, we get the third one for free, so forget about it, right? And I think he was studying, if I remember correctly, the paper, I took a look at it. He was studying like in general relativity, you get your four-dimensional space-time, and you get you can divide it in a foliation with like a space-like surfaces. So I guess he was interested in that. And more recently, I think it was like a year ago or 2 years ago, these three people, Basekin, Galeev, and Nina Shukova, studied chaos for Cartan foliations. And the definition is basically the same. They said chaotic if it has a dense leaf, and the set of closed leaves is dense. So they use closed leaves instead of compacts, but of course these coincide for compact foliations. So these are like this is like the literature on the topic, I guess. Yeah, but so basically one of the things that I was reading their paper and I thought, okay, they seem to think, okay, for group actions we get the last condition for free, so we don't have to worry about it. But I was like, okay, maybe that's not warranted in the general case, because maybe the proof that 1 + 3 = sensitivity does not apply in this context. So that's what I was looking at basically at the beginning. So I'll give an answer to that later. Then, as I said, we're going to use the holonomy pseudogroup as a dynamical model. Again, I'm sorry, I guess everybody here knows it. Just a family of homeomorphisms between open sets that is closed under composition, inversion, restriction to open subsets, and combination. And foliated spaces have holonomy pseudogroups. So basically, I guess everybody knows, but you just take two foliated charts like this, right? And then you have a local homomorphism between the local transversals, and in that way you get like you get a pseudogroup that is like a dynamical model for the foliated space. And usually the problem is that the holonomy pseudogroup is unique only to Étalé equivalence, or this is also called sometimes Hefliger equivalence, or even Morita equivalence. I think I've seen. You want to see the definition? It's not very important. You just get like a family of maps from subsets of X to subsets of U, and the union of the domain is X, the union of the image is Y, and then you have these conditions which basically say if you go from one space to the other and come back, you're still in the pseudogroup, and you can pre-compose and post-compose with maps from the pseudogroups, and you're still in this family. So if you don't, if you know, you know. If you don't know, you don't know. But what you need to know is that this this notion of equivalence is much weaker than, for example, for a group, an isomorphism would be. This is way less rigid. So usually when you study topological dynamics for pseudogroups, so proving that a certain condition is invariant by this is not trivial in general. Yeah, so that's the problem. This is well known, again, people in the topic. Yeah, so let's go, now let's get to defining sensitivity and Devaney chaos for pseudogroups. So, of course, we use like an obvious notion of generation for pseudogroups. So you have a pseudogroup, right, which is like we have a family of homeomorphisms within open sets, and you have a subfamily of that, so you have some maps. And we say it's generating if G is the smallest pseudogroup containing it, or equivalently, you can get all the maps in the pseudogroup using composition, inversion, restrictions, and combinations, right? So if in particular we require that this generating set contains the identity and is closed by composition, restriction, and inverses, it's called a generating pseudostar group. So basically these are the same conditions of a pseudogroup except the combination. So now you have maps defined on non-intersecting open sets. You cannot glue them together. And I'm going to see, well, we're going to see why this is important later. And I think this terminology comes from a paper by Shigenori Matsumoto, if I'm not mistaken. He was studying invariant measures for equicontinuous pseudogroups, I think. Yeah, so the point is like S may not be closed by combination, so that's the axiom we want to erase, right? So why are we going to use it? Why are we going to use this? So let's suppose you're somebody who has never worked on this kind of like topological dynamics for pseudogroups and all that, and you want to be like, okay, I'm going to just generalize naively sensitivity for a pseudogroup. So you can say, okay, let's just add we want a topological condition, so we just quantify over every metric if you want. This is not even important. And then we say, okay, we mirror the definition for groups, and we say there's a positive constant, such that for every point and radius, there is some point y and some map g, such that these points are close, but the images are not, right? So it's the same picture as this. Well, if you know anything about this pseudogroup business, you know this fails spectacularly. And the reason is because of the combination axiom, actually. So if you allow combinations, you basically have too many maps to give any sort of reasonable dynamical condition. And very, okay. So maybe you want to look at a very simple example. So for you have so consider translations on the real line. So you just take x to x plus t, right? And so consider the integer translations. So translations by an integer. And these generate a pseudogroup, right? We just take like all the local maps that can be obtained from this family by restrictions, combinations, blah, 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 blah. Yeah, and to give you an idea of what a generating pseudostar group is just like takes restrictions of this. This would be a generating pseudostar group. But G in general, the entire pseudogroup also contains combinations. And now the problem, so for example, right, we have a translation here and we have another translation here defined on these open sets, and the images are disjoint, so we can just combine them into one map. And suddenly, as soon as you're allowed to do that, you get like, you're allowed to get expansive dynamics. So I think I have a picture for that. Yeah, the problem with this naive definition is that the translation pseudogroup will be sensitive, which is of course insane. So you get any 2 points and you just like combine different translations, and then you get something expansive, which shouldn't be there. This is all well known to people in the area, but it's just like, the reason I showed you this is because if you're not into the dynamics for pseudogroups business, you may think, oh, just get conditions, you write them again in pseudogroups and you get results, but it's not that trivial. You actually have to do some work. And using like very old ideas, so this notion that combinations give problems goes back very far. And in fact, you can see in some books, I think this was a book by Hector and Hirsch, they actually give a definition of pseudogroup without the combination action, because of course it gives problems. And then, Matsumoto, as I said, introduced the notion of pseudo-star group, not notion, maybe the notation. And then more recently, Alvarez and Candel studied equicontinuous pseudogroups with an eye to developing Molino theory for foliated spaces. And they already know the solution to this, which is that you have to quantify this. Before we're taking, so this is basically the same, almost the same thing as in the case for group actions. And before here we're taking maps from the entire pseudogroup. But now what you have to do is you have to put here a generating pseudo-star group, and you have to quantify over all of them. And in this way, you get a condition that of course mirrors the original one, which is extra machinery, and now this is going to work. So now the pseudogroup generated by integer translations is not sensitive, because you can take the generating pseudo-star group, which is only restrictions of the same map, and then you don't get expansion. And you can think, okay, why is that definition good? Well, we get results that mirror the case of group actions, so that gives us some validation, I guess. So we get, the first result we get is that this definition is invariant by Italy equivalences, which we need if we want to apply it to foliated spaces. And again, this is not trivial. This took I don't know, 3 pages or something like that. And the problem is that, as I mentioned before, the Italy equivalences are defined by local maps. And here we have a metric, which is a global thing. So, it's not terribly complicated, but you have to put some work to make this, to make the theorem work. So you have more or less, you get a lot of local information, and you have to patch it up in a smart way. And then, so now if we claim that this definition is actually a generalization of the original one, where group actions generate pseudo-star groups. So how do these two relate when we're looking at the same thing, right? So if we have a finally generated group acting on a compact space, then the action is sensitive if and only if the induced pseudogroup is sensitive. So in this case, our notion of sensitivity coincides with the classical one. And in this case, our pseudogroup is going to be compactly generated. I think I also give I have time, right? Yeah. So again, there's this notion of compact generation for pseudogroups, which corresponds basically to pseudogroups of compact foliated spaces. And in the case of group actions, it's more or less like compact space plus finally generated group, more or less. And this, of course, this notion is also invariant by Italy equivalences. This is well known. I think this, if I'm correct, I didn't write it, but I think it was introduced by Hefliger, I think. And basically, if you want to, it's not terribly important, but you want to look at the definition. You have a pseudogroup, so local maps, and then you have a relatively compact open set meeting every orbit, and a finite generating set for the restricted pseudogroup. So we're restricting here to an open set, and every map has an extension whose domain includes the closure of this, the domain of this. So basically, you look at what happens in a relatively compact open set, and there the maps have extensions, more or less. So this is a condition that is going to, in the pseudogroup language, more or less corresponds to compact foliated space. So we got that for finally generated group actions on compact spaces, the action is sensitive if and only if the induced pseudogroup is. But now, when we drop any one of those conditions, then we get, no problems, but I guess different behavior. So in general, the pseudogroup being sensitive is going to be stronger than the group being sensitive, the group action. And we actually managed to produce an explicit example where the action is sensitive, but the pseudogroup is not. And we have this is the free group, so it's like an action with two generators. So an action by two maps on this, which is just countable union of tori. So something like this. So you have infinitely many. And you can find an action here, and you can construct it using, what do you call that? Linked twists. It's classical dynamical systems. So using that, you can define a group action that is finally generated on a non-compact space, which is not sensitive, but the action is sensitive in the classical sense. But the pseudogroup is not. And on a compact space, you have an action of a non-finally generated group that is sensitive, but the pseudogroup is not sensitive. So as soon as we lose one of these two conditions, we get different behavior, which already hints at the fact that we're going to get different behavior also for non-compact foliated spaces. We can also define equicontinuity for a pseudogroup, and when I say we, I don't mean I, because this has already been done. So you get a point, you get a point of so you can define a point of equicontinuity for a pseudogroup action. So you get a metric and a generating pseudostar group, and if there is some disassignment epsilon delta such that the expansion is bounded by this assignment, then you get SD equicontinuity. So we have this parameter which is a pseudostar group, and we can define almost equicontinuity as that there is some generating pseudostar group S and some metrics such that the points of SD equicontinuity are dense. And so basically this says that almost all the points have this equicontinuous bounded expansion with the same choice of pseudostar group and metric. And then we have before the definition by Alvarez and Candel that says that the pseudogroup is continuous if there is a metric and a generating pseudostar group and an assignment such that the same thing happens, but all uniformly every point satisfies this. So using that, we get basically mirroring the proof in the classical case of group actions, we get a generalization for pseudogroups. So you have a compactly generated and topologically transitive pseudogroup, then it has to be either sensitive or almost equicontinuous in the sense I just described before, or if G is actually minimal, then it's either sensitive or equicontinuous. So it's the same, but note that we need a compact generation here, and this is actually sharp. So we get I'll mention later why, but we got an example of something that is not compactly generated and it has only one orbit which is continuous and the rest are not. So it's kind of strange behavior. And finally, yeah, I think I'm fine. Finally, we're going to define Devaney chaos for foliated spaces using, of course, our work already on pseudogroups. So these are well-known definitions. Just a foliated space is remember, if you're not into these, the leaves are the orbits of our dynamical system. So a foliated space is transitive if there is a dense leaf, and is minimal if every leaf is dense. And this is the new definition we give, which is kind of obvious once you do the work for pseudogroups. So we say, okay, we have these notions for pseudogroups, and we actually prove that they're all invariant by equivalences. So we say, okay, a foliated space is going to be sensitive, equicontinuous, or almost equicontinuous if the holonomy pseudogroup is. Again, the equicontinuous part of it was already done by Alvarez and Candel. I'm just including it so that it's all together. And we get the equivalent of the Oslander-York dichotomy for foliated spaces. So you have a compact and transitive foliated space, then it has to be either sensitive or almost equicontinuous, and if X is minimal, then it's either sensitive or equicontinuous. So you have, like, in the transitive case, so when there is at least one dense leaf, you only have two options. And you can see easy examples of the three, so they're like nicely categorized. So if you have a Riemannian or leaf foliation, then it's obviously equicontinuous, so this case here. You want something sensitive, you can take, for example, the geodesic foliation of the unit tangent bundle of a compact hyperbolic surface. So this is a chaotic action, so of course you're going to get sensitivity in the compact case. And you can also look for, I mean, there's other more complicated examples that do not come from actions that are sensitive, but it's outside the scope of this, I guess. And if you want to look at something that is almost equicontinuous, you can look at the ray foliation on the solid torus, or even the sphere, because basically there's only expansion at the boundary. At the inside points, you know, you don't get expansion. So, you know, you can have easy examples of these three things. Yeah, so after all this, we can, after we've done the work with pseudogroups, now we can define foliated Devaney chaos. So we say that a space is chaotic if, I'm actually gonna make a note in a second. So if it's topologically transitive, which means there is a dense leaf, then second, the set of compact leaves is dense, and finally, the holonomy pseudogroup is sensitive to initial conditions. Now, you may ask, well, why do you choose compact leaves here? And it's clear that it's very restrictive. This is clear. The reason why I chose this is because what I'm going to do at the end of the talk is I'm going to produce an example of a foliated space, a non-compact foliated space that satisfies the first two conditions but not the third one. So to do that, I'm going to start by obtaining examples in pseudogroups and then constructing foliated spaces that have those pseudogroups as models. Going from a pseudogroup to a non-compact foliation with closed leaves is trivial. The problem is when you want to realize compact leaves, because then you have to more or less close them in a smart way. So this is why basically I choose compact here, because it's strong, and then the result I get at the end of the talk is going to be stronger. So I guess more interesting. But of course you can put close leaves here if you want to. Yeah, so then the result we get is that if X is a compact foliated space, then actually topological transitivity and density of periodic, I guess should be periodic leaves here, implies sensitivity. So in the compact case, everything's nice. We're happy campers because everything is familiar. Yeah, but what about non-compact foliations? So basically, this is the counterexample, which I think is the most interesting part of the paper. So basically, we construct a smooth and transversally affine foliation by surfaces on a non-compact four manifold that satisfies these conditions. So it's topologically transitive. There is a dense leaf. And then the set of compact leaves is dense, but the foliation is not sensitive to initial conditions. So this is why I chose compact leaves, because obtaining this here is more complicated than just closed, right? Closed, I think, would be trivial. Yeah, that's not important. So how does this work? So basically, the idea is, well, I mean, if you want to, basically the way we defined it is as follows. We start with a pseudogroup defined with the link twist on infinitely many tori. And then you from that you get like sort of suspension, and you have, I'm not going to explain exactly how because it's kind of complicated, but you have to like cut and paste so that you get these compact leaves here. Otherwise, you know, you have to do some work to get that. And so what about, how can this be not sensitive, right? Well, if you want to like get a geometric picture on how this works. So we get a foliation of a four manifold, right? So we have a dense leaf and a dense set of compact leaves. So you have a locally finite atlas, and this goes from open sets to R2 times R2. And we have some natural metrics on the transversals. So the transversals are going to be R2 with Euclidean metric, and the transition maps on the transversal components are going to be just affine maps. And, but there is a closed non-compact leaf such that every holonomy transformation defined on L is an isometry. So basically you have so basically you can find a leaf and an atlas like that, such that every holonomy transformation defined here, so you get a local transversal and you slide it around, and it's always going to be an isometry. But however, outside of these, it's going to be complicated behavior like compact leaves and a dense leaf going everywhere. So I think that's everything, and we can finish on time. Yay! Yeah. So the point is, there's no butterfly effect around that. So as I said, what I want to, if you wanna, maybe the point is the following. So what I've done is I've more or less translated these topological dynamical notions into foliated spaces. We can find some amusing examples, and we can show that in the compact case it more or less works well. And now I guess the work to be done will be to try to generalize some other condition, dynamical condition, and try to make some interplay between these and positive entropy and whatever. And also, I've chosen to generalize Devaney chaos because it's the most common used definition of chaos as far as I've seen. But there's all other conditions such as linear chaos and so on that look even more difficult to generalize. So maybe that'd be also interesting to do. And I guess that's everything. There's some references if you want to look at these. And I didn't add my preprint, but of course there's a preprint. If any of you is interested, I can give you a reference. And just to finish, I'll just say that it's been an honor to me to be invited here, even though I think I've only met Paul, I think twice, maybe 3 times. But I have a very fond memory of, I think it was 2016 or whereabouts. There was a very nice conference, I think in mid-level. We had a nice wild boar dinner, I remember that. And it was actually my first international conference. So it was the first time I was doing my PhD, and it was the first time I was going to talk, abroad, outside of Spain. And I remember that I gave the talk. I was a nervous wreck. I'm sure the talk was a complete disaster. And even after that, I remember that I left the room after the talk, and Paul was the first person to come and talk to me. And he was very encouraging. So he was like, "Oh, it was nice and all that." So I have a very fond memory of very encouraging words. So thank you for that, and in general, thank you all for your attention. Yes.
I guess your example is of codimension 2, so can you give a codimension 1 example of this?
Yes, that's a very natural question, and I've given this talk 2 or 3 times. I've gotten that question before. I always say I'll look into it, and I never have now because I didn't have time. But of course, it's a very natural question. This is dimension 2 and codimension 2, right? So can you improve that? Can you go to either dimension 1 or codimension 1? I think I have a proof. I haven't written it down and looked at it carefully, but I think it's kind of obvious, unless I'm terribly wrong about something. I think dimension 1 cannot happen, because dimension 1 is basically a flow, more or less. But what about codimension 1? And the short answer is I have no idea. Maybe you can get it, but I don't know. Usually dynamics in dimension 1, when I say dimension 1, I mean dimension 1 on the transversals, so the codimension 1 on the foliation, tend to be very different from higher dimensions. And in fact, usually Devaney chaos is not very well behaved for dimension 1. So the short answer is I don't know, but of course it's a natural question if you can improve this example.
Where is the fact that you're working with the dimension 2, where is it entering in the pseudo-group action? What are the dynamics of the pseudo-group action?
Okay, so the reason why I have dimension 2 is because we use, so basically, so it's not very easy to explain, but I'll try to give an intuitive idea. So I mentioned that to construct this example, I start from a pseudo-group, right? So we have, actually I start from a group action on infinitely many disjoint tori. And basically, how this works is, so you have infinitely many tori. Of course, you have a identification, right? And you have twists here. So basically, a twist, you have like two intervals, one horizontal and one vertical. And what you do is you compose a twist in this direction with this twist in a different direction, right? So now you have is very classical objects, and you get chaos here, but on here you get nothing. This is the identity here. So basically, what I do is I get different twists like that with smaller and smaller domains where this is the identity. So in the end, more or less, you get a point where everything outside of it is chaotic, but around the point you only get trivial dynamics. And the answer is, I know how to do this in dimension 2. I don't know how to do it in dimension 1. But this is where the dimension 2 comes from, is using this as building blocks for the transversal dynamics.
Any other questions? Yeah?
Well, no, it has been intense.
No other questions? Let's thank.
Just a remark. Codimension 1, if the ambient is compact, the union of leaves of compact leaves is compact. So
Sorry?
you need the for the codimension 1 example.
Yes.
You need to be an open manifold.
Oh, for this too, this is open.
Oh, it's open. Okay.
Yeah. Yeah, I showed, but I mean, it's a good point because I didn't say it here. So this is an open for manifold. Yeah, well, it's here actually. Yeah. So for the compact case, of course, what you say, but also, we prove that these first two conditions apply the third here.
Okay. Thank you.
Thank you.
Other questions? Okay, let's thank the speaker again.
Thank you.
And let's thank all speakers today.